thermal control system. So thermal control system is very much is a part of the all the satellite, whether it's a small satellite or big satellite. But depending upon the size of the satellite, the control system might vary. So today, Mr. Barve, he has a lot of experience in designing thermal aspect of different spacecraft. So he will be giving four lectures on this series, and student, you are being a part of the like aerospace. So those who are more interested, probably we can initiate them dialogue with him and do some project or whatever analysis is required. So that is what now is a thermal control design for spacecraft. Mr. Barve, please take over.
Okay. Good morning, friends. I'm SG Barve here. Today, I'll be talking about the thermal control system for the spacecraft. What it contains, I'm going to explain or present in four different parts. Part 1 will basically cover the basics of the thermal control system and the heat transfer concepts, while part 2 will cover the design and analysis of the satellite. Today I am going to cover part 1 and part 2, while part 3 will carry the thermal control elements and the fabrication related activities, while part 4 will cover the satellite testing. So part 3 and part 4 I will cover in the next lecture. So my today's presentation, I will start with part 1, which outline in general gives the concept and basics of spacecraft thermal control system, definition of heat and temperature, basics of heat transfer, introduction to satellites, orbital parameters, temperature specification, satellite orbit and environmental loads, satellite axis definition. Now, the first point, concepts and basics of spacecraft thermal control. Whenever we come across a parameter, what you call as a temperature, or sometimes we call one more parameter as a heat. Now, in any thermal control system, these are the two basic parameters always we come across. One is temperature and second is heat transfer, or amount of heat need to be transferred. Human body average temperature is maintained around 37.5 degrees centigrade by the internal, you can say, heat balance within a body, while the temperature an indicator of level of internal energy within a given body. Many times what happens, as the temperature increases, it damages the human body. That is why many times we worry because of some malfunctioning of some of the system. When we get a fever, our temperature goes up maybe half degree, 1 degree, 1.5 degree. Then our system becomes weak, and sometimes even beyond certain range, it can even damage our human organs. At a lower temperature, which is generally not applicable for human body, for other subsystems, it can reduce its you can say efficiency. Now, with respect to the second parameter, what we refer as a heat. Heat is a flow of thermal energy that takes place from one place to another due to a temperature difference. So we come across, or we observe, or we experience the heat transfer from a body at a high temperature to a low temperature. Now, this kind of thing can be observed in most of the cases, which I will explain in subsequent slides. heat energy, which sometimes we call thermal energy, is created by the movement of particle by virtue of getting heat. The heat energy increases its temperature, and thereby it increases its temperature, causes atoms to move faster, and that causes a transfer of heat from an object at high temperature to object as low temperature. See, for example, if you see there is a bulb which can dissipate anywhere between 5 watt to 100 watt as an example. Now, when we talk about a bulb, when it is dissipating nowadays, we get low voltage or LEDs. They are in the 5 watt, 10 watt, 20 watt. There what happens, it has got its efficiency. Say for example, the efficiency of the bulb is 20%, then rest of the 80% energy is converted into the heat energy. And this heat energy is transferred to the surrounding by virtue of either the convection or by radiation, which I will explain this. Then, an example I just gave as an example of our iron box, which we use in a day-to-day life. There in a box, we have one heater inside. That heater is powered by electric supply. Then the coil gets heated and it increases the temperature of the base, which in turn, by pressing it against the cloth, we do the ironing. Now, one more example just I showed here is a boy or a man is dancing or shouting. Then what happens? Because of the internal metabolic action, he does dissipate certain amount of energy. So that energy, what he dissipate, it will depend on the type of activity he is carrying out. Now, how heat transfer takes place? The basic heat transfer concepts, what we have studied or we are always coming across in day-to-day life, is conduction, convection, and radiation. Why it is important? Because these are the way we are going to use subsequently in the satellite design. Now, conduction is concerned. For example, if you observe that a rod is held in a high temperature source, then the rod gets heated and the energy gets transferred by virtue of conduction through the metallic rod. But by chance, if this rod is low conducting, like a wood or any similar object, then heat will not get transferred. It will start accumulating at certain level, and this at the some portion, if the temperature crosses, that particular portion may burn. So this is the way of conduction. So we always talk about, if it's a metallic, we get a hot shock if it is transfer the heat by conduction. Second thing is convection. When we see some kind of fire, the air around the fire gets heat from the source, and that air becomes a lighter and it goes up and it gives heat to the sink where it may. If you are holding hand, it will become warmer. If you are putting a water with a vessel, water will get boiled. This is the convection. While the third is by virtue of radiation. So even if you are far away from the source, you get heat energy by radiation, which you can experience. Now, the basic differences between these three ways of heat transfer, either it can be conduction, convection, and radiation. How does it differ? The conduction transfer heat is direct contact. Like I told you, you are holding a handle of any container or a pan. That is why many times we use this handle. If it is metallic, you will get a shock. But if it is made up of wood, then you can comfortably hold the pan. Medium, you require a medium because there is a heat flow path. So you require some kind of medium. Move only by short distance. If this is too far off, the heat cannot be transferred because subsequently I'll tell you by equation as the length or the length, the what it has to cover, if it increases, heat transfer reduces. The rate of heat transfer is governed by virtue of thermal conductivity of that object. For example, if it is a handle or if it is a metallic rod, its conductivity decides the rate of heat transfer. While in case of convection, which in day-to-day life we experience in our house, or maybe, for example, if you see around with a small breeze, we dry our clothes, or when we put any kind of things outside, it get dried. That is one best example of convection. This transfer of heat here is by the flow of current in the liquid. For example, if you see here, whenever the object in the container, it get heated, the water molecules or the liquid molecules which are at the base, they get heated, they become lighter, they go up, and they replace with the heavier molecules. So that is how the currents are created by virtue of convection in a liquid. So it does require some kind of medium. It moves relatively larger distance because if I got larger quantity of liquid, then it can comfortably go from one end to another. The rate of heat transfer is governed by convective heat transfer coefficient, which probably in the next slide I will explain it. So in case of radiation, this transfer of heat takes place by virtue of electromagnetic waves. Here, you do not require medium. For example, whenever we stand outside in a hot sun, we do get a sun rays directly from the deep space falling on our body. Luckily here what happened, we do have air around the earth, but even if you don't have air around earth, your body will get sun load directly from the deep space, from the sun, by virtue of radiation. It moves at any distance. There is no limit of distance. Only thing, as you move away and away from the sun, its intensity keeps reducing. The rate of heat transfer governed by surface optical properties. For example, the body or our surface, what we are holding outside in front of the sun, its optical properties will decide what quantity or what portion of energy will be absorbed by the objects. Now, these are the basic equations which we come across in the case of conduction, convection, and radiation. In case of conduction, it is governed by a law called Fourier's law of heat conduction. Here, heat transfer equation says Q is the amount of energy transferred from one object to the other object is K into A divided by L into the bracket T1 minus T2. That means source temperature is T1, sink temperature is T2. K is the conduction factor of the given object. For example, if I am holding an aluminum rod, this aluminum do have conductivity value in the range of 120 to 180, like what we call aluminum 2024 up to commercial. If you have any other high quality aluminum, that conductivity can be beyond 180. So the K plays very important role in case of conduction. This is what I was telling in the previous slide. A is the cross-sectional area of the given section. If you have got any rod, then its cross-sectional area A, pi by 4 d square will give you A. While the L is the length it needs to move from one end of the rod to the other end of the rod. This is how the Fourier's law of heat conduction gives heat energy transfer from object 1 to object 2. Second, when we come across convection, which is generally called as Newton's law of cooling, is Q equal to HA into delta T. Here, one should keep in mind, H is the convective heat transfer coefficient, which we were referring in previous slide for the convection. This value can be as low as 5 to 7 watt per meter square for a still air if you are standing outside with no breeze and just as a still air, that is air is not moving, then that value can be in the range of 5 to 7. But when we switch on fan, for example, when you are standing in front of fan, then this same heat transfer H can be as 100 to 200 depending on the speed of the fan. A, one should remember, A is the surface area here. See, whatever the source is having, A is the surface area of the given object. It is throwing heat to the other object. T1 is the temperature of the source, while T2 is the sink temperature. This is the part 2. Then third is the radiation. Stephen-Boltzmann law basically tells the heat transfer that takes place by virtue of for a black body, an ideal body as given, that is Q equal to sigma A T raised to 4. Here sigma is the Stephen-Boltzmann constant, which is given in most of the books as 5.67 into 10 raised to minus 8 watt per meter square Kelvin raised to 4. While A is the surface area of the given hot object. And T, one should remember, T here is in Kelvin, not in degree centigrade. In previous two cases, it is only delta T. By virtue of that, it can be any unit. It can be degree centigrade, degree Kelvin. But in case of Stephen-Boltzmann radiation, this T comes as a parameter in degree Kelvin only. Now, this is the same example, similar example, whatever I told you earlier. Simply I am repeating here how the heat takes place by conduction from the hot object container to the hand, or it can be convection by the molecular heating and replacing back, or it can be radiation. These are the three basic modes of heat transfer. Now, many times we do ask question to ourselves, why is thermal management is important for the spacecraft? This is a typical picture of a mathematical model I shown for one of the satellite. Now I will go ahead with what you call the importance of heat transfer for the spacecraft. Now, heat rejection is via radiation in the space or within an object is by conduction, which is totally different than what we call terrestrial, means on the ground, which is dominated by convection. So in deep space, when the satellite is launched at a predetermined altitude, you say for example 300 kilometer, 500 kilometer or 800 kilometer, the parameter of conduction and convection radiation only come to the picture. Radiation is absent there since there is no air, there is no medium there. So one should keep in mind for the deep space, parameters 2 are only come to picture is conduction and radiation. The sun is a very hot object and it produces continuously an energy of 1350 watt per meter square. In fact, this particular energy, what we call the solar intensity, it does vary from season to season. It is approximately 1.3 kilowatt to 1.4 kilowatt from summer to winter. This is the amount of energy we near Earth satellite receives at an average distance of what they call one astronomical unit between the sun and the earth. The earth is a comparatively cool object. In fact, earth should receive the energy from the surrounding by virtue of solar energy coming from the deep space from the sun, as well as certain amount of energy when it gets in the earth's atmosphere. Certain amount of energy it absorbs and remaining is getting reflected back. That reflected back energy is called albedo. That parameter will come little later on. So by virtue of this particular earth atmosphere around the earth, this sun energy when it absorbs, the average temperature of the earth, it remains around close to around 250K. In fact, this 250K is the average temperature one should keep in mind. In fact, it does vary once you go towards the North Pole and South Pole, it further reduces because the amount of energy, sun energy receives, it reduces. That's why North and South Pole, we see the ice cubes. Now, there is no air in the space for a fan to blow around unless you are willing to build a pressure vessel. Earlier days, Russian satellites, they used to design such that they used to make use of convection. For that, what they used to make it, they used to make an enclosure for the satellite, and that enclosure is a sealed, totally sealed proof, and they used to put some kind of a gas, and they used to maintain the temperature by virtue of a fan, so that temperature of the satellite can be maintained. But it has got its own limitation. There is every chance you will it is prone for the leaks of that gas inside the enclosure, or you have to give big penalty for the heavy mass. So generally we do not come across this kind of design. Then third, one more aspects is heaters required power usually mostly during the eclipse period. Eclipse period is that period when satellite is moving around the earth. Most of the time he receives the sun load, but when he go behind the earth away from sun, that is called eclipse duration, and that is mostly applicable for low earth orbit satellite. So during that time you do require some kind of backup power which is provided by battery. Bigger battery means more mass per volume. So our design should be such that your battery size should be as compact as possible so that mass comes down per volume. Now, one definition I'm going to put it here as a definition of thermal control system. Now, definition of thermal control system is mainly the maintenance of the temperature and temperature stability of every atom on board satellite within the predefined limits during all mission phases, and it should use the minimum spacecraft resources, that is the weight, volume, and the power. Because here it is much more important in the sense that whenever we talk about temperature, why this temperature stability is important, probably in subsequent slides I will give in detail, because if you cross those temperature limits, the subsystem do not work efficiently. Every subsystem has certain range of temperature during which they work efficiently. Beyond certain range, their efficiency comes down, or even below certain temperature range, they becomes inactive. Now, introduction to satellites. Now, ISRO has developed a spacecraft bus. Bus in the sense that is a satellite structure which houses the different subsystem required for the satellite application and the satellite control. So these buses are all varieties of things are there for nano satellite, for small satellite, or for the big satellite. Now, for in general, the thermal design concepts are remains same, only its criticality changes from nano small to big satellite because it need to handle different level of power. Otherwise, basic concepts of thermal design remain same for nano satellite, small satellite, or big satellite. Nano satellite, what you call as Indian nano satellite bus, a small satellite bus, what is developed by IMS 1 and 2, while big satellites, there are IRS buses are there, or insat class of satellite I1K, I2K, I3K buses are there. So bus is basically is the structural design that houses varieties of satellite subsystem packages what are required and other related material or accessories. Now, with respect to the payload, now most of the time we are coming across for the low nano satellite or medium satellite is a remote sensing thing. In the remote sensing area, we can have an image taking cameras which can be panchromatic or can be middle infrared or it can be long wave infrared. Now, panchromatic camera has got certain limitation that they like our house camera what we take images at home with either with or earlier days cameras that surface image need to be taken has to be eliminated. If it is dark, you cannot take images of those objects. Same thing is applicable for panchromatic kind of satellite. Those payloads, they can operate only during the daytime when the area is getting illuminated by sun. While middle infrared and long wave infrared, they can work in the night also because they are working in the microwave area. Now, there is no hard and fast rule. General thumb rule is used for the satellite category, whether it is a nano satellite or is a small satellite or is a medium satellite or is a big satellite. These are all thumb rule. There is no hard and fast rule. If we see, for example, nano satellite is referred as that satellite which mass is approximately around 10 kg, where the bus mass is 5 kg and payload is 5 kg. Where the mainframe load, that is power it can generate, is of the order of 15 watt. These are the typical values I am giving. One need not stick to those values exactly. It can be few watts this side or that side. Then second part is the small satellite, where the mass can be of the order of 100 to 150 kg, while the mainframe load, that is the power generation, what it can create and support for 100 to 200 watt. Medium satellite like Cartosat, what I showed you earlier, it is up to some 700 kg class satellite where the power generation is of the order of 500 to 600 watt. While the big satellite, like very first time what we used to talk or recently RISAT kind of satellite, they go about a ton and above, actually up to 2 ton they can go, 1 ton to 2 ton. So their load or the power what they are handling is in the range of 1 kilowatt to 2 kilowatt. This gives a reference for somebody in which range the satellite is coming. There is no exact hard and fast rule to stick those numbers. Now, one more parameter which is important from thermal point of view is the orbital parameters. These orbital parameters are very important for any satellite design. How it is important? Because what happens when the satellite is going around the Earth, it's how the satellite is moving around the Earth, it decides which orbit is following, how the different load pattern will come on a different surfaces of the satellite, during which time you will get eclipse, and how the satellite is going to experience the set temperature variation on different panels. One category, what we call is 3-axis stabilized with Earth pointing sun synchronous satellite. At the beginning of the ISRO's, most of the satellite, they used to be only Earth pointing satellite. So one surface is always pointing towards Earth, while the solar panel will be tracking sun such that maximum power generation takes place. Then second category, recently last 10 to 15 years, we are coming across most of the satellite what we call sun oriented, sun synchronous satellite. Here what happens, one surface it looks towards earth but it not exactly sun oriented. During certain portion of the orbit only it will see toward the earth like a earth pointing mode. Otherwise, most of the time it will be away from the earth, only viewing towards the earth, while the solar panels are in the fixed position and always all pointed toward the sun, such that maximum power generation is generated during the orbit. So what they do, they generally hold the satellite in this position, and the satellite moves around the earth. Whenever they want to take imageries, they rotate the satellite such that the camera will look exactly to the target of the earth, whichever portion we need to take images, and it comes back after the image portion is over. That's why most of the recent satellite we come across, they are three-axis stabilized, sun-oriented, sun-synchronous orbit. Now, this orbit altitude, it can be 450 to 870. In fact, we started our first satellite like IRS, and even before that, they are all around 900 kilometer categories. Now, slowly they have come to know, depending on our application, we keep the satellite in a range of 4 to 817 or that order. Then we have most of our applications in near Earth orbit. They will satisfy this particular altitude. Altitude is that particular height from the average height from the surface of the Earth. Now, orbital type, I told you sun synchronous orbit, it is called sun oriented. Then orbit inclination, if you want to be orbit to be sun synchronous, the intention of sun synchronous is that particular satellite will come to particular portion of the earth regularly at the regular fixed timing. For example, they call the equatorial crossing time 6 to 12. Now, if want somebody at 6 o'clock or 9 o'clock equatorial crossing time, that particular satellite need to be sun synchronous satellite, because as the sun moves in an imaginary plane, what we call an ecliptic plane, and the satellite moves into the orbit around the earth, this angle between the sun and the earth and the orbit plane, it remains nearly same. There we call it sun synchronous orbit. Its intention or advantage is whatever imageries of the earth given surface I take today and tomorrow, it remains similar under the similar surface illumination. So that is the advantage in sun synchronous orbit. Now, equatorial crossing time is one of the important aspects of the low Earth orbit satellite for the application point of view. See, most of this application, what we come across for the agricultural purpose, they are in the range of 9 to 10:30. While when we talk about ocean related applications, they are close to 12 o'clock. While there are certain applications in the microwave area, they launch the satellite because they are not depending on the exact emission. So they are launched at the 6 a.m. or 6 p.m. The mission life of the satellite that will be decided depending on its design, anywhere between 6 months to 5 years. This is a typical number for the low Earth orbit satellite only. Now, one more parameter what we come across is the temperature specification. Now, why temperature specification is important? Because satellite and assemble, that is an total combination of various subsystems which operate at its best at the temperature or temperature range for what they are designed. See, for example, you must be knowing that most of the electronics packages, they work very efficiently at the room temperature. While as the temperature of that package keeps rising beyond certain range, then its efficiency or its dissipation start rising, and then its efficiency of those components then comes down, and that particular package fails at early stage. That is why individual package wise we need to maintain at a limited temperature range. Similarly, that whenever the satellite, that particular object temperature goes low, then also certain components, see for example some diodes or some of the chips, they get crack. So low temperature also they can create some kind of problem. So most of the packages, most of the subsystems, they need to maintain in a given temperature range for uh, uh, the package to work at its best efficiency. Satellite thermal control deals with thermal balance between heat generation, transportation, and heat rejection, so that temperature of the satellite can be maintained within the specified limit. Now, when you say, just now I was telling you that most of the package, electronics package, for example, they work very good or very efficiently in the range of 0 to 40. But best range for them is room temperature, like what we experience at our home, it between 15 to 25, 20 to 30 in that range. As you go lower and lower, there is no problem, they still work. But if it comes below minus 10, minus 20, minus 30, there is an every chance some of the pins or those related components can crack, joint can crack. While the temperature goes beyond certain thing, like lithium battery, its efficiency comes down. So in range of temperature for an individual subsystem is important, as the range, for example, electronics packages are 0 to 40. Batteries, nowadays what happened, earlier days we used to use nickel cadmium battery, which need to maintain in the range of 0 to 10. Nowadays most of the satellite application, they use lithium ion battery that need to maintain in the range of 10 to 20. Propulsion element we need to maintain in the range of 15 to 40, while optical payloads, what I was referring earlier, some of the cameras on board, they need to maintain in the range of 15 to 25, while the reaction wheels, which controls the satellite attitude, it need to maintain in the range of 15 to 40. So in thermal design, there are different aspects, what we call thermal design range. Then we call acceptance, because what happens when we design certain thing, we need to give certain temperature range on either side for the testing of the satellite, so that because of some uncertainty while evaluation or by any other measurement, if it creates some kind of uncertainty in the measurement of the power or the situation or the configuration, then it should be able to sustain those temperature range. So that thermal design to acceptance, minimum 10 degree on either side is provided as additional range for acceptance testing of the packages, and that takes into consideration uncertainty in the measurement, uncertainty in the estimation of the temperature based on mathematical modeling or actual measurement or any other environmental uncertainty. Over about that, we add another 5 degree to take care of, because any new package is developed will be totally new to the design. So for that purpose, additional operating qualification temperature level, they add another 5 degree for the qualification purpose. Now, in case of camera, see, one is what I told you is a temperature range. Another thing is temperature gradient, that at any given instant of time, delta T among the different elements of that camera should not exceed 5 degree. In fact, this is the old configuration. Nowadays, they keep this range as low as 2 degree. Now, most of the cameras, they are maintained in the given specified limit of 15 to 25 with a narrow temperature range to be maintained in the range of 2 to 2.5 degree. Now, one more parameter which matters is the orbital environment for satellite. Now, when we talk about satellite, I told you earlier, I hope this cursor you are seeing, this is called polar orbit. Polar orbit advantage of the near Earth or satellite is when the satellite is moving in the polar orbit from North Pole to South Pole, our Earth actually moves from west to east. So, in that process, the satellite do cover the whole globe by its own because its rotation remains here only. Only the Earth moves from the west to east. In that process, imageries can be taken globally in a given duration of time. For example, 10 days, 20 days, or 30 days, depending on the individual camera capacity of the satellite. This is called near Earth orbit satellite. While there are geostationary satellite which you must come across as Indian National, your INSAT class of satellite, Indian National Satellite. They are communication satellite actually. So they need to be at close to 36,000 kilometers. So with respect to Earth, at any time, their movement speed or they move around the Earth and the satellite movement, they match each other so that at any time, if it is for India, that satellite you feel relatively always it is in front of India because its moment of speed at which it speeds rotates around the Earth and the Earth movement they match at 36,000 kilometer altitude. There are certain satellite nowadays they are flown in navigational purpose and inclined orbit also. Now, next one more parameter when the satellite moves around the Earth, especially for the low Earth orbit satellite, we see that energy balance which we need to consider under the steady state is Q generation, means the amount of energy is generated by virtue of different electronics packages and its activity internally. Then the amount of solar energy, the eliminated portion of the satellite it receives. Then albedo is the portion of the energy when it falls in the earth atmosphere and gets reflected back. That is called the albedo load. While is thrown back to the deep space, is thrown back to the satellite surface, and only portion of that energy is written by the satellite, interrupted by satellite, that is albedo. And third is the solar sunshine load is by virtue of Earth's average temperature, it gets and it gives to the satellite. That is called planet load or Earth-shine load. So satellite receives direct solar load, solar energy that is reflected from the Earth's atmosphere on the different surfaces, and the planet load from the object. These are the three different load. All the external surface of the satellite it receives, and by virtue of its limited area, the temperature and its variation will take place. See, for example, again, I will come back to that load. For example, I told you that average solar load do vary depending on season from 1.3 kilowatt to 1.4 kilowatt. Now, this do vary because of the season. From summer, we get close to 1.3 kilowatt, while in winter, it goes as 1.4 kilowatt. The albedo means the portion amount of energy it reflects back. That percentage is around 20% to 40%, depending on the Earth surface. Near the equator, it throws more, while as you go toward the north and south, it keeps reducing by virtue of ice portion of the Earth. Now, this average value generally used as 0.3. Earth-chain load is by virtue of average temperature of the Earth. I told you around 250. It gives this load to the satellite depending on the altitude of the satellite, means how far it is from Earth's surface, is anywhere between 250 to 250, 150 to 250 watt per meter square. And the same solar load, how it varies, a typical value just I gave it. See, for Earth, it is around, average I told you is around 1.4 kilowatt, uh, uh, close to 1.3 to 1.4 kilowatt, while Venus, it is almost around close to 3 kilowatt, 3.2 kilowatt, while if you go to Mercury, the the energy level from sun what you get is as high as 9 kilowatt. So if you go from any satellite near the satellite, once it goes towards the Venus or worst case under Mercury, he need to sustain very high temperature. It's a surface, and we need to have special treatment or special insulation how to withstand such a high, very high external sun load. Now, one more thing, just I will tell you that if the satellite goes away from sun, you say instead of Mercury, Venus, Earth, it goes to Mars. Actually, Mars, it is other way around. Solar intensity, instead of getting around close to 1.4 or 1.3 kilowatt, it becomes half of that actually, close to zero point 0.7 kilowatt per meter square. So the thing is, power generation reduces and the amount of energy
Uh,
is.
Mr. Barve,
Ah,
this strip is showing,
ah.
stop sharing. Next is a hide. You just click hide so that overlapping can be avoided. No. That you just, yeah, right side. Just after stop sharing, so that the student can see the full. No,
No,
not
I will
this
go
one.
back.
No, this hide. That is right.
Now, if you see here, same thing, how the variation of albedo and Earth-chain load for the near-Earth orbit satellite, it varies right from albedo 450 because it's a sun load, it gets variation from 450 and approaching as low as 0. This is by virtue of only the altitude and its inclination with respect to the Earth's surface actually. Now, one should keep in mind this both the parameter albedo and Earth-chain are important for the low Earth orbit satellite only. It is not important for the satellite like INSAT, which are as far off as 36,000 kilometers. The reason being, at that altitude, the amount of energy what can be received by virtue of, for example, Earth-chain load is very small. So that impact of that is total, is really, is if you call in terms of temperature, is negligible. That is why in most of the geostationary satellite we do not consider the impact of albedo Earth-chain on the satellite surface. Now, this completes my part 1 where I just say the introductory portion. Now I will go to part 2 where
We can have
actually,
some 5-10 minutes break if you want,
okay, just 2 minutes.
and the student can ask some question
I,
on the part
I, I
one.
think that is the best actually. I suggest that they can ask any question in this
Yeah,
portion, or
student,
if they,
please go ahead.
or if they want, they can ask the question of part 2 end also, because I'm going to
Yes.
stop with part 2 today.
Yeah, that's right.
Hmm? Choice is
So,
there.
so student, any question?
Sir, Anirudh sir.
Yeah,
Sir, how thermal boundary layers are formed, sir? Like,
See, boundary layers concept basically comes in convection, and that is a phenomena you come across only in the ground. It does not come with picture like Prandtl number and all thing. No? It comes only on the application which is on the ground, not in the space.
understood, sir. Thank you.
any other question? Other students, why? You have to participate.
No problem. You can part 2 end
Yeah,
also again you can ask question. There is no problem.
yeah, yeah.
Any question you can ask. Can we go ahead?
Okay. Okay, I think they are not asking any question.
No problem. End of
Yeah,
2 seconds, I think we'll stop. Or
yeah.
if
Please
we
go
give them
ahead.
choice later on also.
Yeah, yeah, that's all.
Part 2, I'm going to cover basically the spacecraft thermal design and analysis. These are one of the important aspects of the satellite design purpose, because this designs what kind of design we are going to do, what difficulty we are going to face to maintain the temperature of the satellite, and what are the constraints for the given satellite configuration and its altitude or inclination. So I'm going to cover in general introduction, spacecraft axis definition, input parameter, what is required, mathematical modeling, and temperature estimation. Now, thermal designer, whenever you say anybody is a thermal designer, his involvement starts from the inception of the project to the end of the project. Because once he is involved from the satellite conceptual things starts, then he will be knowing what is the satellite orientation, satellite altitude, satellite configuration, or it need to handle the power deception level. Then, depending on that, he can give significant input for the satellite configuration. For example, if the battery is there. Now, battery, as you have seen earlier, some of the batteries need to be maintained in very narrow temperature, 10 to 15, 10 to 20. Then you cannot keep such object or such subsystems anywhere you require in the satellite. You need to maintain where the satellite surface temperature will receive a least solar load or no solar load, with other two loads are also to the minimum level. So some such parameter. See, for example, there are certain objects where, like a gyro we call. Now, gyro temperature, absolute temperature is important, but much more important is its temperature variation. So we need to put subsystem like gyro at a certain location only, so that its temperature variation during an orbit is as minimal as possible. Because if the temperature variation is more, then stability and what the feedback it gives, it significantly affects. So these are some of the parameters. Like this, there are many such parameters, like a payload, where you should put a payload, what you should do for the payload location purpose. Those inputs are given by the thermal design. So thermal design provides those advantage of various satellite configuration also. For example, somebody may say, I want to keep the satellite in inclined orbit. In inclined orbit, thing what happens, satellite moves much more faster, then it can have more payload operation. But only problem is, there you cannot have that certain areas should not see sun, that kind of thing is not possible. While the what we call sun oriented sun satellite or earth oriented sun satellite, certain area always remains away from the sun direction. So that is the advantage. While in case of inclined orbit, you cannot have that kind of benefit, that certain area should not get sun load. That is not possible. Only thing is, it can cover much more area if your satellite is launched and in inclined orbit. Thermal designer points out any criticality for the subsystem depending on the satellite location, which just now I told you actually. Now, satellite axis definition holds a key for the external load variation on different surfaces, because when the satellite configuration is finalized, then we will be knowing how the satellite moves in the space around the earth with respect to the sun and the earth orientation. Now, this will configure that which surfaces will get sun load for what duration, during which portion of the orbit, or which portion of the satellite can be totally away from the sun direction. And certain portion, certain areas, actually they do not even get the what we call as earth-chain load as well as albedo load. So those are some of the concepts are important, and that is why they called a typical axis definition X, Y, and Z as yaw axis, pitch axis, and roll axis. These references are basically taken from a boat. You must be seeing a boat is going in a river or in the ocean. Generally, yawing and pitching, these are common terms I use. Rolling is not there, because rolling is then people will go into the water actually. But these are the axis definition basically taken from the board, that yaw, pitch, and roll actually. Now, these are the typical one satellite picture. Just I am showing how the this configuration is taken, such that roll, yaw, pitch. Once you follow moment of roll toward the yaw, the third axis is pitch. This is what defined, and this is very important, because when satellite moves around the Earth, then certain area becomes toward the sun side, while the certain area becomes totally away from the sun. So this is very important from the satellite configuration point of view. Now, thermal designer receives various inputs related to the spacecraft. See, beginning of the satellite, when the configuration starts, or when they start discussing with different subsystems, then as a thermal designer, he need to take what is the satellite orbit altitude. Altitude is important because, as I told you earlier, that lower and lower altitude means you will get more and more albedo and earth-chain load. Inclination is important because satellite in which category, that you will get to know. An orbit type, which I told you earlier, it can be sun-oriented, it can be inclined orbit, and sun-oriented sun-signal satellite. Different panels, size, material, you will get details, because panel size and its material that decides the modeling purpose, or you can say so-called your internal conduction purpose, or its modeling purpose. These parameters are important. List of subsystem packages. You know, there are some dozens of packages inside satellite. You can have more than 60-70 packages inside satellite, depending on the satellite configuration. Then the package location in the satellite, which is equally important. Then its dimension, what is the X, Y, and Z, that is different direction. Then power distribution of the package. Then the power cycle. Some of the packages, they distribute only certain duration, so it's a cycle, or it's a particular cycle if they follow, that you should know. Then package interface with the panel. See, some of the package will have very good interface with the panel, so that heat conduction path becomes very simple. If they are isolated, then heat flow path reduces, the temperature of the package will go. So these are some of the parameters are very important, and above parameters also include the similar inputs for the payload. Payload is nothing but an instrument, the purpose for which the satellite is launched. For example, I told you at the beginning that certain cameras are mounted in one of the panel. They take the imageries. So those cameras and the related electronics together, they call it the payload for the satellite. See, some of the transponder, you see, transponder for the inside of the satellite, they form the payload for the communication satellite. So for some of the micro and antennas, they have antennas on one side of the satellite. They form the payload for the, along with its processing electronics, as a payload for the microwave satellite. Now, factors which are affecting temperature of the spacecraft. Now, internal, there are thermal dissipation. What is the dissipation level of the packages? See, some of the dissipations are only momentarily, only for 5 minutes, 10 minutes. Some of the dissipations are continuous. So we should know all their configuration clearly, whether they are intermittent type or continuous. Then second thing is the location of that particular package, where it is located, location of dissipating element, and the degradation. Degradation means some of the packages, by virtue of its temperature or sometime with the time, they vary. So what is the criteria, or what is the way they degrade or change the power distribution or power dissipation? That is important. Then dimension of a given package, dimension is equally important, because bigger the package, its area is more, then its radiating area is more. Weight is equally important, because if the weight is more, and suppose that particular package has got momentarily for short duration dissipation, then mcp into delta t, that inertia is more, and then temperature rise reduces. So weight is become equally important for the limited duration power dissipation package. Localized heat flux is sometimes power dissipation is important, as well as the flux means what is the size of that component or that package and its power distribution value. Smaller the package and dissipation is more, its flux level will be high. So you to take care of those things. I will tell you those things subsequently in the next lecture. What we take care, how we take care of the high flux packages actually. So that is called heat flux. Then allowable temperature range. Every subsystem as a as a input to the designer, they always get either from catalog or from the past experience or from the some of the internal. They do testing, based on that they give the allowable temperature range what that package can sustain. Then heat flow path. We need to decide how the heat flow path takes place within a package. See, for example, most of the packages either they are made up of aluminum or magnesium alloy nowadays, but what should be the thickness of that package, which will improve the heat flow from the, all the components to the wall of the package and to the base of the package, and from the base it will go to the panel and the in plane, how it flows. That heat flow path is very important for the maintaining the temperature of the satellite. Now there are certain external parameters which causes for the temperature control. One is orbital parameter. I told you attitude. Attitude in the what orientation is holding with respect to Earth or with respect to Sun. Then depending on the satellite altitude, its eclipse duration is decided. Typical value of the most of the Earth near Earth satellite is around a range of 30 to 35 minutes duration, where for this near Earth satellite, close to 95 to 100 minutes one orbit duration exists. So you have eclipse period of around 30 to 35 minutes duration. Orientation to the load. See what happens. We need to know how the satellite is oriented with respect to different load. It can be albedo shine or it can be solar load. Then depending on the season, solar intensity does varies from 1.3 to 1.4 kilowatt. I told you, from summer to the winter, because you are aware that by virtue of satellite movement, satellite comes closer and goes away during an year, and the average solar intensity that is varies in the range of 0.3 to 0.4, 1.3 to 1.4 kilowatt per meter square. And albedo and planetary load variation on different surfaces during an orbit, and available radiator area. What happens? Some of the small satellite, your amount of energy it need to throw, it gets limited, because the satellite size itself will be very, very small. So radiator area also becomes one of the parameter. Now, what is done in a spacecraft thermal design? Spacecraft is simulated into number of control volume of simplified geometry. What is simplified geometry? They can be either rectangle, they can be triangle, they can be trapezium, that kind of thing, they do it. And that radiating surface of the control volume are considered as isothermal node. Isothermal node means what? If you see, for example, any one surface, for example, this, then that particular rectangle is taken as a uniform temperature for radiation purpose. But theoretically speaking, there is a gradient from this particular element to this particular element. There is a gradient It can be from higher to lower or low to higher, depending on its location, power source available, or external load. But for a given radiation purpose, estimation purpose, the given that element is taken as so-called uniform temperature for the radiation purpose. Because for radiation, we have got a fourth term, raised to 4. So for simplicity, in the mathematical modeling, we take that as radiating surface of the control volume as isothermal. Isothermal node in the sense, for a given element, temperature is uniform in given element area. Energy balance equations are written for each element. Whatever I showed you, individual element is taken at one element, and a thermal balance equation, what I'm going to show subsequently, is written for each and every element, that how much energy it receives, how much energy is getting transferred, is radiating, and it is generating power. The energy balance equations are solved simultaneously. Here, one more thing, what happens, we need to, suppose you have got altogether something like around 1000 or 5000 nodes, then you need to solve all those equations simultaneously. It is called simultaneous equation you have to use. There are varieties of different methods are there, different softwares are available to solve the equation as a function of time. So as a function of time, once you are calculating temperature, then it gives the energy stored in the given element as a function of time. It will raise the temperature, it will cool down at the rate of change of energy stored as a function of time. In case of Earth orbiting satellite, this is applicable. In case if we one olden days we used to fly what we used to call as spinning satellite, means when the satellite is moving around the Earth, satellite is to spin around one particular axis. By virtue of spinning, that energy gets you can say equally distributed on a different surface. Then we do not need to calculate the time-based thing. We can calculate the steady state temperature, average temperature of the object or that particular element. So these are the typical picture I just showed, how the elemental thing is calculated. For example, this is solar panel, how the temperature distribution takes place from one end to another corner. We can estimate. This is applicable for satellite also. This is area is called radiating area, what we call OSR area, what I will explain in the next lecture. That is called radiating area for the given panel. So this is how the modeling is carried out. Now, this lump parameter concept you use, what I told you earlier, is that given element is taken its mass m into Cp, and it is calculated its temperature rise or thing by virtue of its thermal capacity, its size, that will decide its temperature variation during an orbit, depending on if it is external load, whether it is internal load, it is well connected to the neighboring element or not. That is what it is considered in the lump parameter concept. With available input parameters, see what happens when the satellite evolution is going on right from the beginning, then we whatever input available at that particular instant, we keep taking those inputs available for the analysis, and different input parameters related to size, material, power input, and detailed mathematical modeling, what I showed you earlier, is carried out. And we subsequent pictures I will show you that once you are calculating those so-called different equations, we do get the temperature distribution, and sometimes if it is steady state, you get average temperature. If it is a so-called oriented satellite, then we get temperature variation during an orbit. Then various software I told you are available for the estimation of those temperatures as a function of time. Now here what happens, basically we use most of those software as a finite difference method, because in next slide I am going to show that the radiation term is coming. There you have got a fourth term based on our Stephen-Boltzmann equation, T raised to 4. By virtue of that, what happens is that this equation becomes little complicated. We cannot use the finite element method, and that is why finite difference method use which is so many times what you call it iterative kind of thing, and that is why we use most of the finite difference method related softwares for the calculation of those all varieties of equation. So based on the preliminary thermal analysis, the design is finalized for the various subsystem, and subsequently detailed thermal analysis is carried out, which surface is going high temperature or low temperature. Depending on then again we need to change the design if it is essential. So these are the typical modeling what I showed earlier. This is another satellite how the modeling is carried out actually. Uniformly it is. So we'll know from one end to other end how the temperature distribution. Now, thermal analysis is the need to do the energy balance equation, that at any given element is the heat conducted from all the control volume. All control volume is what? For example, if you take any one surface, then what energy it gets from the neighboring all its element. That is the control volume. If you get this is particular node, if I am considering, what is the energy received by virtue of conduction from its neighbor. That is by virtue of conduction in contact with the control volume under consideration. Heat received by radiation. See if it is within a enclosure, then this particular given element is seeing some other element, how the radiation takes place within those objects, within the one surface to other surface, provided they see each other. So these are the things comes in the radiation. If they are in the same plane, only then you will have some kind of reflected radiations. Otherwise, what portion it gets radiation is the surface what is seeing the other. Heat generated within, see some of the element, they may have some electronics package. That means they will be getting some kind of portion of the heat generated by that package that is carried to that particular element by virtue of thing. Now, these remaining three, what I'm going to think, four for example, they are applicable if that particular element is seeing deep space. See, you get solar absorption load provided that surface is seeing the deep space. If it is external surface seeing a deep space, then you get certain amount of solar energy, albedo energy, or Earth load energy, provided you are seeing in a deep space and you are oriented toward the solar direction. And obviously, once it is external surface, it will be seeing the deep space also. It will be losing heat to the deep space depending on its temperature. And after solving this, you will know the energy stored is mCp into delta T by delta T, which will give the temperature. This is basically internal energy. How this internal energy keeps varying during an orbit will give the change in temperature for the given object. The same thing, conduction portion again from one object to the other object. How this getting coupling to the different surfaces is shown here. Similarly, radiation, even one surface here, one surface here, how they radiate with each other will decide the radiation. So here that one term what I told you earlier, immediacy of the satellite, immediacy of the given surface is important for the radiation coupling or radiation estimation purpose. Thermal analysis carried out for various satellite configuration and temperature distribution is obtained for each condition. Here what happens is, when we talk about satellite, when satellite is ready for launch at the launch pad, generally what they do is they maintain that at the launch pad they provide the air conditioned air. So by virtue of that, temperature of the most of the subsystem are maintained close to 25 degrees centigrade. But the time of liftoff is declared just 10 minutes before that, they switch off the AC system.
No, if you want, just you can have some 5 minutes
no
break.
problem. Slowly I will.
No problem.
No problem.
Okay.
I will talk slowly. Then what happens, as the liftoff time is declared, then they switch off this AC system, and satellite is by the time 10 minutes before, 15 minutes before itself, satellite would have already switched on. Then satellite dissipation will decide how the temperature of the satellite will change. Now by this time, this whole satellite will be enclosed in a heat shield. Now the temperature of the satellite, once it takes liftoff, up to the injection, how it varies, that need to be estimated. So that is for the beginning of life. Now here what happens, you may be aware, or maybe subsequently sometime I will, if it's possible, just show you that at certain height, the satellite heat shield gets separated. Now heat shield gets separated, then what happens? The satellite actually gets exposed to the deep space, where it will start getting the solar load, orbital load, or Earth-send load, depending on the orientation of satellite. And there what happens, it is in vicinity of the Earth. Maybe, for example, you talk about this heat shield separation takes around 115 or 120 kilometers. Little bit air is there at that altitude. So convection also little bit helps, but mainly cooling by virtue of deep space cold. And if it is exposed to sun, suddenly temperature start rising because satellite surface is getting exposed to the deep space with the sun load. So this trajectory, what we call from liftoff up to the injection, that is called the launch pad or initial phase temperature distribution. One need to estimate based on the satellite configuration. Now, beginning of life, sometimes we call one more concept, when satellite is getting injected into the given altitude by the fourth stage, or in case of inside third stage, then satellite keeps rotating around the Earth, and it's achieves the, you say for example, its final stage. Then whatever temperature it is achieving is the, we call as beginning of life. The reason being, it's most of the optical properties. You see what happens, because of the deep space, because of the repeated following the cycle of low temperature, high temperature, and all things, the optical properties of the external surface keeps degrading. And by virtue of that, what happens is its optical properties keeps, for example, solar absorbance conceptually, that keeps increasing. And by virtue of that, at certain end of the time, then it goes to the end of life. Means you say, for example, satellite is going something around 15 years of life. Then most of the properties, optical properties, get degraded. So the temperature or the input given to the satellite is under the worst case condition, at the end of life. While beginning of life, it is the least input is given as far as the external surfaces from the external solar load. Also, it happens in beginning of life, many payload related packages will be off actually, because satellite would not have started its operation completely. So power dissipation inside satellite also comparatively low. So you may experience the low temperature for the beginning of life. So you need to calculate beginning of life under such condition, end of life under the worst case condition. And one more thing they call, during the course of time, whenever you call our satellite going around the Earth, because of some reason, if it experience some kind of problem, some kind of uncertainty, some kind of unforeseen experience, or some kind of thing you experience, then what they do is they switch off many packages and they put the satellite in a non-orientation position. That is called safe mode. Under such position, satellite will generate sufficient power generation which will support the satellite dependent subsystem, but simultaneously many system they switch off so that load on the satellite can be reduced. So this is a concept in the safe mode. Then they may analyze what was the problem, what was behaving like this. See, for example, some of this, either it may be wheel speed or any other thing, you can say some of the package is not behaving as expected, why it's behaving. Those things they analyze this, and then they go back to the satellite orientation as they expect at a later stage, depending on the wheel or depending on the thruster. So that is called safe mode. Safe mode is a portion comes under the some worst case difficulty when we face. And transfer orbit, I told you earlier, this is basically applicable more of a insert class of satellite, because unlike low earth orbit satellite where you need to know the only transfer orbit, you say for example initial 20-minute kind of thing from the injection going to the orbit and achieving orbit in another half an hour, altogether maybe around 1 hour kind of thing, while that need to be estimated how the different surfaces undergo the temperature variation on different surfaces or different subsystem. That is transfer bit for the low Earth satellite. But in case of INSAT, what happens is satellite is generally injected into the orbit, which is highly elliptical. Just for information I'm telling, which is not important for a low Earth satellite, is the satellite can be injected into the orbit as something what you call 300 to 10,000 kilometer highly elliptical orbit, and then slowly every 2 days or 3 days they'll keep doing the orbit this is the thruster firing, orbit correction, they will do it and keep rising the orbit altitude, which finally they could get it around close to 36,000 kilometers. So this is a matter of almost like a 4 days or 5 days. So those kind of things, once they are going, then they need to do the transfer orbit in detail for all those 4 days for the communication satellite. That is not applicable in case of low Earth orbit satellite, where you see that low Earth satellite altogether you will have of the order of one orbit 60 minutes or around 1 hour, or worst case you can say one orbit which is close to around 95 minutes to 100 minute duration. So that you need to calculate for the initial phase transfer orbit, what you call for the low Earth orbit satellite. Now this is what one of the typical orientation I told you that is applicable for the satellite. Once you talk from the launch pad, when the heat shield is separated and it gets in. These are all things will be there. This is called the surface where the satellite is getting integrated with the pore stage, and different small satellites and related electrons they mount it here, and whole the thing you need to estimate for the transfer orbit for the so-called low Earth satellite. Now once a satellite is injected, now all the thing will go, only satellite will move around the Earth and it will have impact, and subsequently you will have that what we call solar panel deployment, and all this thing get detached from the satellite and satellite alone will go around the Earth. So this is how this takes place. So this is, I'm completing my today's presentation here. If you want any specific question with respect to this as on today's presentation, I'm ready to ask any question. But these are the things I'm covering in part 1 and part 2 as a portion of introduction to satellite thing and the thermal design analysis actually. Any specific
Nice, nice, Barve. Students, you can probably discuss some part, whatever you understood, whatever you have not understood.
Sir,
Please
can
go
I
ahead.
ask?
Yes, yes. Please go ahead.
Sir, practically no state is unsteady, like steady state, no, sir. Like practically.
No, steady state means what happened. For example, I told you when any object is moving around the Earth, and this I'm talking basically for the low Earth orbit satellite, the different external loads it gets externally on the given surface, it keeps varying. Sometimes what happens is dissipation level also keeps varying. So that is what it causes the temperature variation during an orbit. This is applicable in nowadays. Olden days, what used to happen is the satellite used to keep, because the spinning satellite has got better stability from the attitude point of view. So those days, since we were the initial phases, satellite used to keep in spinning satellite. Otherwise, any oriented satellite or any spinning any satellite which goes around the Earth always will have this kind of different load or different dissipation, and thereby different temperature distribution and variation during an orbit.
Sir, practically, like no unsteady state has to be accounted now, sir. Like while doing thermal analysis for
I'm
any.
talking about unsteady means what? It is not stable. See, for example, any one particular temperature, suppose you are having now, after 10 minutes, the temperature will not hold good. After 10 minutes, by virtue of its orientation, where it is going, because I told you, approximately close to 100 minutes, one satellite, one makes one orbit, complete orbit rotation from one equator end to back to that place actually. So all external loads, all the thing keeps varying. So that way it is unstable only as far as the temperature is concerned.
Sir, can we calculate it like using mathematical formulas? Any
Mathematical problem, I told you, no? Basically, varieties of things are used. See, for example, you must have heard our mathematical, many softwares are available. They are using different methods. See, for example, simple method I will tell you is Runga-Kutta method. You must have come across in numerical analysis, Runga-Kutta method. So, Runga-Kutta method is a similar thing what they use actually. So, different locations and different element. No? That kind of thing is calculated as a part of the theoretical analysis actually.
understood, sir. Thank you.
Other students, please.
Agarwalji, I will suggest one more thing. In case anybody has any question at later date, they can send it by mail to you. You can direct me.
Yeah, Karthik is actually interfacing.
Okay, you can tell him to collect
I'll pass it on to you.
He can pass it to me. You know my mail ID, otherwise I'll pass it on to him.
Yeah, no, we have. Anyway, Karthik knows your email ID.
So anytime you require, he can send because sometimes.
What I want to suggest students, see, this is one area because these students are from aerospace.
Okay.
Thermal and structure is one area very close to them.
Correct.
If they want to study a little bit more, they should actively participate, and that will be useful for them. Electronics part, very less people may be experienced there.
Okay.
But particularly mechanical, there must be. I understand the student must be more on mechanical background.
Correct.
And they have studied some of the mechanical subject, so it will be more useful.
Correct.
Student, please, anything? Okay. Okay, Barve, thank you very much.
Okay. Anything they can pass on through Karthik. They can send to him. Mail, you can request them. Any question, then I will reply back to him actually.
Okay.
Thank you. Thank you.
Thank you, Karthik. Huh?
Thank you.
Okay.
Thank you, sir.
Okay, thank you.
Next is on Monday.
Monday afternoon 1 to
1:30.
1:30. 1:30.
Okay.
Thank you then.